Good. Hello, everyone. My name is Ning. I'm a postdoc researcher at Northwestern. Today, I'm going to talk about our work on proving unsatisfiability in zero knowledge, adding a little bit of flavor of cryptography to this workshop, and I hope it can serve as a good appetite for your lunch. Okay, this is a joint work with Timos, Bill, Ruzika, Iria, and Xiao. So at the beginning of this talk, I want to give you a big picture and explain what motivates us to combining these cryptographic primitives to automated reasoning and formal methods. So verification now has been widely used in practice, and it can go beyond self-interests. This verification can be required by many outside entities. One typical example will be this centralized software distribution and verification platforms, where the developer will upload their software to this centralized marketplace. And this marketplace will do the verification and make sure this software doesn't contain any malicious code or vulnerability, and then distribute all this software. And after all this verification is finished, this software marketplace will distribute the software to their user. Such centralized platforms provide a solution to a lot of problems, such as this attack in supply chain. However, it also raises issues. One of the biggest issues is we put a lot of trust to this centralized marketplace. For example, first, the developer needed to trust that this centralized marketplace respect the privacy of their software. That means the developer should trust that this centralized marketplace will not reveal the critical component of their code to any third party. At the same time, the user should also trust this centralized marketplace indeed do the verification of interests and in a proper way. In addition, such centralized marketplace also raises the issue of monopoly, as they can promote whatever software they want to advertise. In real life, such kind of issue is getting attention, and many legal efforts has been made. And we ask ourselves, can we remove such centralized verification and distribution and replace it using some alternative? And that's all of this story motivates us about developing this privacy-preserving formal method toolchain. This toolchain actually a protocol that between the user and the developer. So the user directly interact with the developer. The user can verify if the software or program provided by the developer satisfies certain expected property without reviewing what the program or the software are. And now I want to using an example to convince you that proving unsatisfiability in the zero knowledge will be the first step towards privacy preserving formal method. So this is a standard way to do some standard way to do verification. So we have a program and we have some specification. This specification defines expected behavior of the program. And then we put the programs and the specification to some standard program analysis tool. This tool will give us some formula. And the unsatisfiability of the formula says that for any input, the output of the program will be the factorial of the input. And then we can send this formula to some solver. If the formula is indeed unsatisfiable, then the solver will output hopefully output some unsatisfiability certificate. And when the formula is first order logic formula or propositional logic formula, the certificate will be a resolution proof. However, as we said before, when the program becomes private, when the program is private, that means it's encrypted in some form, in some approach. And so is the formula. So the formula also becomes private. So is a resolution proof. Think about a resolution proof that is encrypted. Under this case, how can you still validate this resolution proof and make sure this resolution proof is indeed correct? How can you do that? And that's our question, and there are some generic ways that you can apply some cryptographic primitives, i.e. there are knowledge proof to this certificate checker, so this checker can consume such encrypted resolution proof. This is a generic way. However, we do some experiment and found this generic implementation of certificate checker using cryptography primitives is not impractical and doesn't scale at all. On the other hand, our ZK UNSAT scales to the formula, real world formula that's related to related to verification task of system driver. Now you may ask why we can do that beyond or why we can do that like such scale for such largest instance. I want to give some brief about the ingredient of our scalability. What we did here is we encode clause using polynomial over a finite field, and then reduce checking resolution proof to checking relations between all these polynomials. Now you may ask why I suddenly do drama about polynomials over a finite field. So essentially this checker will do what the certificate checker doing is just checking relations between a bunch of polynomials. But why polynomials? Why we select polynomial? Why we don't stay on the using language of a set to describe clauses? The reason is that there are efficient protocol in the zero knowledge to check relations between all these polynomials in finite field, and they are also well developed and engineered library for the implementation of such protocol. That's why we finally decided to using polynomials to represent clauses, and I will elaborate our approach in the next few slides. In the next slide. Okay, in the next of my talk, I will give you a little bit background information about zero knowledge proof, and maybe we can skip the part for resolution proof, and then explain our protocol. And finally, I'm going to talk about a little bit of future. So let's give this resolution rule. I want to stop here for a while and ask you a question. So the question is, given a resolution proof, how can you validate this resolution proof is correct? How can you check the validity of the resolution proof? So the resolution proof will be in these forms, where C4 is a clause, is a resolvent, and the 0, 1 means by applying resolution rule to clause 0 and clause 1, you got C4. Given you such kind of resolution proof, how can you check the validity of the proof? No one? No, just like forget the finite field polynomial. Just like we have a x2, we know this is x2, and we know the 0, 1. We know we derive this x2 by applying resolution rule to clause 0 and clause 1. Giving you proof like this, how do you?
Yeah. Yeah. Okay. I just use resolution. I don't understand what the question is.
Yeah.
I mean, at first, I'm canceling x1, and then I'm canceling x1 again in the next two, and then I just have to cancel x2. Exactly.
Actually, why this is because it's so what we are doing here is we know this x4 is obtained by applying resolution rule to clause 0 and clause 1. Then we fetch these two clauses, and as you said, we just eliminate the neutral x1, right? Sorry, x2, x1, right? So we just applying this resolution, and then we check. Okay, by applying resolution rule to these two clauses, we indeed get x2, which is C4. So we check. Okay, the C4 is obtained in a valid way. So just these two simple steps, and we can repeat this for C4, C5. C6 until we meet a contradiction. That's quite easy to check. It's quite easy to check the validity of resolution proof in the plain text Like if we don't talk about a finite field, if we don't talk about their knowledge, we don't have any concern about privacy, then it's quite easily to achieve, to check the validity of the resolution proof. Now, when the resolution proof become private, how can we still do that? And now first want to give you some background information about their knowledge proof. That's what we will use in the next for achieving checking to achieve checking resolution proof in a privacy preserved manner. So in the first slide of their knowledge proof, I want to refresh your memory about prover and the verifier, because I know they have a different meaning in verification community. And so using this Coke or Pepsi example. So in this problem, the prover want to convince the verifier that I know a way to tell Pepsi or Coke. And the verifier said, oh, I don't believe you because they don't differ at all. So how can, and then prover, but if you show me how to do that, then I will trust you that you really know such approach. And then the prover said, I don't want to show you how I will do that, but I want to prove to you that I know how to do that. So there is a very cute solution to solve this problem. If you don't know, it's in a probabilistic way. If you don't know, I will leave this as a homework, or you can ask me offline. But the point of this slide is trying to convince you that there are two parties in their knowledge proof, and there is a prover and there are prover and verifier. Both of them can be malicious and adversarial, in the sense that the prover may cheat about his ability to tell Pepsi and Coke, and the verifier may try to know what the approach is. Now I'm going to introduce their knowledge proof in a more mathematical way. So let's say we have a public circuit. This circuit is known to everyone, and the prover claims that he knows assignment that make the circuit output 1. And he wants to convince the verifier that he knows such assignment that make the circuit output 1 without revealing any information about what such assignment is. On the other hand, the verifier wants to validate the prover's claim about her knowledge of this such assignment, and he tried to learn what the verifier tries to learn what such assignment is. Both prover and the verifier can be malicious. As I said before, the prover may cheat about his ability, he cheat about his knowledge of such assignments that make the circuit output 1, and the verifier is trying to learn what such assignment is. So that's the setting of their knowledge proof, and there are multiple approaches to achieve their knowledge proof. One of the things we use here is leverage this authenticated schemes. So authenticated scheme, you can think for now you can think it as an encryption schemes or encryption scheme. So authenticated value is a ciphertext that will hide underlying value first, and then it enables the verifier to check the relations between this underlying value over the ciphertext. So the verifier doesn't know what the underlying value is, but only using the ciphertext, the verifier should be able to check the relations between the underlying value. And finally, it also prevents the prover from cheating about what underlying value is. For example, at the beginning, the prover authenticated or encrypt a bit 0 and send the ciphertext to the verifier. And then after that, after a while, a bit, okay, let's say it authenticated a bit 0 and send the ciphertext to the verifier. And after a while, he told he tried to convince the verifier that the ciphertext, the underlying value of the ciphertext is 1. Then the verifier should be able to detect that the verifier is cheating and not trust the prover. So that's the authenticated schemes we use as a property we use. And once we have such authenticated schemes, what we can do is we can have the prover first authenticate or encrypt all value the values over all wires. Remember that the prover knows what the input of the circuit should be. So the prover should be able to compute all the value over the wires. And then the verifier check if the input and output of each gate is indeed consistent over the ciphertext again. So the verifier doesn't know what the underlying value of the ciphertext. So the verifier should not be able to know what the input is. And finally, the prover review what the value of the output circuit is. And if the value is indeed 1, then the verifier trusts that the prover indeed know an input that makes the circuit output 1. Does any questions here? Okay, so if using the same way, we can also verify the relation between polynomials, since we can check the relations, like arithmetical relations between value. We can also use the same approach to verify relations between polynomials. So let's say we have 2 private polynomials. What private polynomials? By private polynomials, I mean the coefficients of these polynomials are secret and encrypted. So it's authenticated in the authenticated schemes we mentioned before. And the prover try to convince the verifier that the relations between polynomials. For example, here he tried to convince the verifier these 2 private polynomials equals to each other. What the prover will do is having the verifier first select a random value and send this random value to the prover. Then the prover prove these 2 polynomials evaluation at this particular random point equal to each other. If these 2 private polynomials evaluation at this random point equals to each other, then with large confidence, we know these 2 polynomials equal to each other, even we don't know what the polynomial are and when the coefficients of these polynomials are private. Using the same idea, we can prove a little bit more complicated relation between polynomials, such as this product relation, and this relation we call the GCD relation, and this we call the shifting relations, because you just shift the polynomials for a while. And we use these relations are used to later in checking our ZK UNSAT. But if you got a little bit lost here, don't worry, I have a takeaway. So the takeaway is verify using their knowledge proof. The verifier can verify relations between private value. That means the value are encrypted or authenticated. So the verifier doesn't know what the underlying value is. The verifier only knows the ciphertext. And the verifier can verify the relation between private value and private polynomials without learning any information about what the values themselves, the value themselves. So that's the takeaway of the knowledge proof part. And I hope everyone is still there. Okay. Okay. And another takeaway is we have implemented and well-developed library for checking relations between private polynomials that we can leverage to to design our protocol.
Is it probabilistic or is it for sure?
It's probabilistic. Yeah, probabilistic. So you don't have you need to, for example, here. For example, here you just select a random point, and the probability that the confidence you get about the equivalence between these polynomials is 1 minus d. D is the degree of these 2 polynomials. So so it's 1 minus d over the f. F is the field, the field size you are talking. The polynomials is over. So we are talking about the finite field. Yeah. So it's a probabilistic, and you can increase it by, like, for example, selecting 2 random points, have more rounds. If this doesn't satisfy, it's not satisfying. So now we know their knowledge proof. I want to concretize a little bit more about our proving unsatisfiability in the knowledge setting. So in our setting, the prover knows a resolution proof and for a formula. And he tried to convince the verifier that the formula is indeed unsatisfiable, while keep the information about both the formula and the proof private. And the verifier tried to validate the prover's claim about the unsatisfiability of the formula. And both of them can be malicious in the sense that the prover may cheat about the unsatisfiability of his input formula. For example, if the prover formula is not unsatisfiable at all, the prover may use a fake resolution proof. So it may not be like if you don't have some using some cryptography tools, then it may not be detected since all the resolution proof is encrypted. So if the protocol is not secure, then it's possible for prover to cheat about the unsatisfiability of the formula when the input formula is not unsatisfiable at all. At the same time, the verifier tries to learn the information about the proof and the formula. So we want to keep the information about the proof and the formula private. As a reminder that because our ultimate goal is to verify private software, and if this formula and the proof may reveal a lot of information of the software as a starting point. So that's why we want to keep the formula and the proof private. As I mentioned before, to check if a resolution proof is correct, there are two simple steps. One is just fetch the premise clauses. One is check the application of the resolution rule, if the application of the resolution rule is correct. So we want to implement these two steps in a privacy preserving manner. So how can we do that? We achieve and implement these two steps based on two cryptographic primitives. One is zero knowledge protocol for integer comparison. One is zero knowledge protocol for checking polynomials relation that I have explained before. So that's a high-level design overview of our work, and I will begin with how can we check application of resolution rule in zero knowledge using polynomial. So the high-level idea here is you think the clause as a set of literal. Once you think the clause as a set of literal, then you can encode the set of literals as a polynomial where the root of the polynomials is the literal itself. Oh, it sounds a little bit confusing because it's just think the literal as some fine. You can think the literal you can encode the literal as some finite field element. Then you can represent the set of literal using a polynomials where each root of these polynomials are the encoding of the literal. So how can we first encode the literal as a finite field element? It's like we use let's think the finite field element as a bit string. So we use
What's the K? Like it's
K is a security parameter. So it's not only for security parameter. If you think like we mentioned when we're checking the polynomial of the equivalence between polynomials, K is 2 to the K is the size of finite field, and also the K is the length bit of this, or the length bit of this element, and so the K should be greater than the bit length of the size of all possible literal. Okay, so the first bit of this encoding will be the sign of the literal, and the rest of it will be the binary representation of the index of the literal. So that's we had the encoding schemes from a literal set to finite field elements. Once we have this encoding scheme, that's the encoding scheme we used in our implementation. But any encoding scheme that satisfies these two properties will be good enough to be compatible with our data set. That's the encoding scheme we have in our protocol. So once you have encoding schemes from literal to finite field elements, then you encode the polynomial, the clauses using polynomials, where, as I said, each root of these polynomials is encoding in the literal, is encoding of the literal in the clauses. For example, if the clause is x1 or x2, then corresponding polynomials will be x plus 2 to the k minus 1 plus 1 times x plus 2 to the k minus 1 plus 2. This 2 to the k minus 1 is because the highest bit of the encoding is set to 1, since x1 and the sign of x1 and x2 are positive. So the highest bit is set to 1. And and here we have another example where one of the literals is not x1. So that's why here is x plus 1, because the highest bit is set to 0. Okay, now we have polynomials for clauses. To convince a verifier, this is one step of resolution is valid. One step of resolution is valid. The prover also need to prepare a pivot polynomial. What is pivot polynomial? So pivot polynomial is for pivot literal. So pivot literal is just a literal we eliminate in the resolution proof. We call this pivot literal. And the pivot polynomials are nothing but degree 1 polynomials where the constant is the encoding of the pivot literal. In this example, the pivot polynomials are x plus 2 to the k minus 1 plus 2 and x plus 2, because x2 is x2 and the negation of x2 are the pivot literal. So the prover prepare all these polynomials for resolvent input clauses and the pivot literal and checking the relations between all these polynomials. It's a little, if you think if it's a little bit complicated, just what I want to explain is in the language of a set. So this is what happens when we're checking the polynomial, but what we essentially do is checking the relations between clauses in the language of set, this relation in the language set. So that's what we are, all the drama we are doing here is trying to prove the relation between clauses in the language set. To summarize how we check one-step resolution is using this example, we're having the prover prepare all the polynomials encoding for input clauses, resolvent, and the pivot literal, and then authenticate these polynomials using the authenticate schemes we mentioned before, and send the ciphertext or authenticated value to the verifier. And the verifier checks the relations between all these polynomials. And what essentially the verifier checking is checking the relations between clauses in the language of set, as I highlight here. So that's how can we check how can we validate one step of resolution when we encoding the clauses using polynomial. And the reason we're using polynomials to encode the clauses is because once we have them in their large setting, this checking can be implemented and achieved very efficiently. So that's how we check resolution, one-step resolution. But now we also need to fetch premise clauses from resolvent or input clauses or clauses in the input formula. This actually this actually can be done in using a protocol that proposed 2 years ago. That's so you can verify read-only array operations in their knowledge. I will skip the technical details of how can we verify read-only operation in ZK. If you are interested, we can talk about this offline. But the takeaway is we can indeed fetch or do some read-only operations to over an array in their knowledge without reviewing what the element is and which index we are accessing. So that part of information is also protected. And we also have a check. We can also check application of resolution rule using polynomials encoding of clauses in their knowledge. Now we have both of them. Let's see what's the performance in practice. I have been saying that our ZK onset scale to real world instance. So it turns out that our protocol, there are two features that affect the performance of our protocol. One is this width. Width is the maximal number of literal a clause in the proof can have. The reason why this width will affect, or why the width of the proof will affect our ZK onset is because if you think the polynomial we use to encoding the clauses, the width actually is the degree of the polynomial. And that is the size, you can think it as size of the polynomial. So that's why it's the width of the proof will affect our ZK onset. Oh.
So question, the length of the final proof is not one of the parameters you need to somehow preserve privacy for, because it looks like you're going to go over the whole proof, right? So I will know how long the proof is. That's not a concern.
Yeah, it will be revealed. So the length, you mean the number of resolutions?
Yeah, the number of resolutions that this you have to reveal to me. Yeah?
Yes, you have to review, and the width you also have to review. But okay. you can do some padding. For example, there are things in the proof. You have a bunch of clauses. Some clauses may, for example, contains 10 literals. Some clauses contains 2 literals. You need 2 literals. Then you need to pad your proof to you need to pad all clauses, encoding clauses to up to the 10. So that to hide the width of the the distribution of width of the literal.
Hi, yeah, I might be making a fool out of myself, but I'm just going to ask it anyway. So my understanding with these zero knowledge proofs is that effectively you're proving that there's a program that executes correctly, and this program is effectively an unrolled circuit that unrolls in this case up to 8,000. Is that correct?
No.
So you basically unroll this circuit to 8,000 length and prove the correctness of this program that you executed correctly.
It's not. We are not verifying the correctness of the you mean what the program? You mean the program we have the first picture, or the program just for checking resolution proof? The
checking itself would be effectively modeled as a program. The checking, the checker itself is effectively a kind of a program that is executing and updating its own state, and eventually, and arrives at the empty close, which is what you're looking for, and now you're happy. The problem is that for zero knowledge proofs, if I understand correctly, what you do is that you unroll this state all the way to the right. Okay,
yeah,
I get a nod there. That's good. Okay. So yeah, this gets unrolled all the way to the end, and you effectively have 8,000 steps that now this zero knowledge proof is effectively verifying with these narcs and zk snarks and zk starks. You didn't quite say which one it was, but I'm just going to assume one of them. So it does this kind of stuff. And my question is, like, because there needs to be a question here, is that how does this work with the 8,000? So because 8,000 is nothing, basically. We're going to have millions here.
Yeah, I'm going to show more. This is like I want to say we take less than 1 minute to check this proof. Oh, okay, I know it's quite small in the stat community, but I'm going to show what's a larger instance here. Yeah. Okay, that's the verification task sorry.
Yeah, well, just one more thing. Like, I understand this will convincingly prove that you're refuting some CNF formula. So how do I know, but there has to be some connection to, I mean, you could have cooked up whatever, right? You could have cooked up not X and then pad with junk. And it's like, how do I know that you're refuting something that I'm interested in? Does the question make sense?
You actually ask a question about the future work. So that's our one work we are doing now is, since you want to make sure that you are the prover are not dealing with some random formulas, is that we can give any unsatisfiable formula. So there is a gap between the program of interest and the formula you are the verifier is trying to check the unsatisfiability. So you need to prove the refinement relations between this formula and the formula that is encrypted and the program that is encrypted. So this refinement relation verification checking should be also implemented in zero knowledge, and that's one thing we are now working on. Yeah, thank you. Thank you for asking this question. Yeah, and that's okay. Let's get back to the evaluation. That's the result we got. So the unwind is a value for how, if you know the bounded model checking is how do we deal with the loop. And as you see that the ZK onset can check the formula unsatisfiability of formula for verifying system drivers, say for system driver verification within 5 minutes. And that's for this system driver verification formula of system driver verification. And we also benchmark. We also benchmark even larger instances here. So, and the limit here is when the width is about 1,000 and the length is about 600K. Then the machine we use I posed in the first slide will run out of memory, so the process got killed. But we recently have a work to use a computing cluster to even improve this result, so that instead of one machine, we can have a multiple machine and run this resolution checking and then checking the consistency between different components. So that's the result should be further improved. Okay, let me conclude this part of my talk. So privacy preserving for methods is really in demand. And also we can encoding the proof and the clauses using polynomial so they can be checked very efficiently in a privacy preserving manner. Finally, what ZK onset is practical and can verify this real world instance. And now I want to talk a little bit about the future. Recall that the title of this workshop is about satisfiability. But what I have been talking about is unsatisfiability. Now let's get back to the topic of this workshop. So so we actually have considered solving in privacy preserving setting as a first place. And the setting is when there are two parties, they have their input formula and they want to check the conjunction of their input formula is satisfiable or not. However, both of their constraints can be private things. Like for example, if you think these constraints are personal schedule, then that will be reveal a lot of information and privacy. So we want to protect the privacy of their input formula. And we have this preliminary result that using multi-party computation, which is a protocol in cryptography to achieve such set solving privacy preserving in privacy preserving setting. What we did here there is we're using a matrix to encode the formula. Here is like we have -1, but essentially we are doing is using a binary matrix to encode the formula. So all these operations happens in DPLL can be reduced to linear scan over this matrix, which is expensive, very expensive. But it can. So why we want to have a linear scan is to hide the index access, so that we can protect the input formula's privacy. And we also implement some heuristics. One is DLS, which aggressively need to assign the literal that will satisfy most clauses. One is rand. This just select a random undecided literal and then assign it a random value. And also it's a weighted random. It's still random selection, but to give some weight about each decision. Both of why we implement these three heuristics because they are quite friendly in this privacy preserving setting. That's why we have these three heuristic as this preliminary result. However, I want to show you this result, which is very depressing. So ignore this parameter here. I want to say all instance we have here is a small to medium size instance, set instance. And as you see, it takes about hundreds of thousands seconds to solve this small to medium instance when we want to enhance the privacy. And yeah, you may think this picture comes from decades ago, but no, it's happened last year. And we also benchmark using this. We also use KSAT to solve this benchmark, and this since that needs hundreds of thousands seconds to solve, KSAT only needs 0.02 seconds. So it's depressing, but I want to remind you that SAT solver, this KSAT, they involves decades years of engineering and theory, but this will be is a first work towards SAT solving privacy preserving setting. And we want to ask ourselves, can we find better heuristics when it comes to privacy preserving setting or better data structure to represent the formula? That's the question we really want to answer, and to improve the SAT solving even when even when we want more privacy. So thank you. And if you have any questions, please don't hesitate to contact me. And this repo has all code we have. And I'm also on job market. If you are interested in hiring, please contact. Yeah.
So a question, in all of your settings, like the formula is part of the secret, right?
Yes.
Which you don't want to reveal. I just want to point out one slightly crazy application that you might already be solving, which is like a commercial proof logging, okay? Which might actually be a problem. Like, why would you not expect Cplex and Gurobi to want to implement proof logging in their MIP solvers? Well, we all know what instance they're solving, but the secret sauce is, of course, their amazing, their amazing heuristics and why they solve the instances so fast. And of course, if they would release the proof log, then you could reverse engineer and I can build my solver to be equally efficient, okay? So you could argue that maybe to be commercially viable, you would like I know what instance you're solving, I can verify your proof, but I have no idea what the proof is. Am I making sense?
Yeah, I think that.
And that's sort of, you sort of have a baby version of that problem solved already. But because if I know the formula, then I could probably verify your original fetch operations maybe. And then I just know that apparently you have some proof and the zero knowledge proof is going through. So apparently you did decide on SAT, right? So it seems that you solved my formula honestly, but I have no idea what your solver did. And so Cplex and Gurobi will be very happy.
Yeah, thank you. I think that's very motivating.
Yeah, time for one quick question, Made.
Very basic question. It looks like you're implementing this these pseudo knowledge. So is there an implementation of just checking satisfiability? I've given this original.
The implementation is what?
So given a formula and there is an assignment. I want to convince.
I think if you want to check satisfiability, that means you have an assignment that makes the formula.
Yeah, I know that I have an assignment, but I have to tell you that this is an assignment.
Then you can use standards like their knowledge proof in MP.
Is there an implementation and people have done that or no? Not interesting.
I think there are. So, but there are even more like optimization for that. But I'm not aware of like any particular any implementation, like especially for formula assignments. But for any, since that is MP company, I think many problems.
Oh, is it?
Yeah.
I mean, there's a whole range of work, I think, on like efficient implementations of probabilistically checkable proofs, for instance, which would be exactly this, right? Where you're optimizing like the length of the proof and you're optimizing like, although the formula has a billion variables or a gazillion variables, you only want to read like, at most 1000 bits from this proof. And then you still want to know with 99% probability that indeed you had a satisfying assignment. And some of these things actually go into like some of these new cryptocurrencies and stuff. So like one of our former esteemed colleagues in the proof complexity community, Eli Ben Sasson, who is now like getting filthy rich on doing this kind of things instead. I think it's like very, very cool work where you take like the highly non-trivial theoretical PCP constructions and then really squeeze out the juice and you get it to run in practice. So this is.
I guess it's a dumb question, but you said the verifier can be malicious. So what if the verifier just refuses to believe that the polynomials were equal?
Okay, here with the malicious model for the verifier is the verifier tries to learn. It's not the goal. The goal
No,
of
I understand that you wanted the verifier to be malicious in one way, but the verifier does have to say, well, your proof was convinced. The verifier can't just say, I deny that that it worked.
Yeah, what I show, sorry, what I show here is interactive version that the verifier directly interact with the prover, but we can also, like in this work is also compatible with some zero-knowledge proof backend that is non-interactive. So the prover can generate a proof and publish, generate a zero-knowledge proof for unsatisfiability of the formula and publish it. So make it public. So even when the verifier want to deny this, want to deny the unsatisfiability of the formula, since the proof is public, there are some, like you may use some other technique, like for example, voting schemes. So to a bunch of verifiers that if most of them are not malicious, then you can come to the right result. Is that yeah.
But it's like, okay, so you're saying that, yeah, that's a good way, right? Connecting to what Don said, I guess, like clarifying the model. Is it, should we think of the verifier like this is honest but curious kind of?
So I think it's not honest and curious. Like it's in a setting where the verifier may need to, follow some protocol. You can think it, yeah, okay. The answer is partially yes. But I want to emphasize here is when you say curious and honest but curious, you usually the verifier need to do several steps that violate the protocol, and it usually happens in multi-party computation where these two parties want to compute a function over their inputs, and the goal of this verifier or the other party that violates the protocol is trying to mess up the output of the function. That's the goal. But I don't say, but yeah, the goal is yes. You can think like they are curious, honest about curious. So the goal of them is to learn information about the input formula. Yeah.
Okay, so let's conclude. Thanks a lot, Ning, again. We're going to have lunch break now, and we'll meet at 2 p.m. for knowledge comparison.